Hi everyone, my name is Ilya Yesin, and in this talk I will discuss a class of driven, strongly interacting topological systems. I will show that despite the absence of long-lived quasiparticles in the system, it forms a long-lived quasi-steady state exhibiting universal transport. The interplay of topology and far-form equilibrium dynamics became an important arena of research in recent years. Although topology was first discovered in equilibrium, it finds surprising manifestations in periodically driven systems. For example, non-trivial topological bands can be induced by resonant drives in trivial insulators, giving rise to Fouquet topological insulators. Another example is time crystals, where an interplay of interactions, periodic drive, and disorder gives rise to a rich phase diagram with topological phases hosting Majorana modes. In this talk, we focus on another class of topology that is exclusive for Fouquet-Bloch systems. It relies on the periodicity of their quasi-energy and quasi-momentum domains, which in one dimension has a shape of a torus. The topological invariant is defined as the winding of the quasi-energy around this torus. Here we focus on one important member of this class of systems known as the topological or towless pumps. The towless pump comprises a bipartite lattice with a modulated in time Steyer potential and dimerization of the bonds in such a way that the single particle gap never closes within a driving period. The original model focuses on a regime where the drive is in a topological phase, meaning the Steyer potential and the dimerization encircle the origin. The drive is adiabatically slow, and the static system is an insulator. In this regime, the drive induces a quantized pumped current through the system of exactly 1 electron per driving cycle. The Fouquet spectrum of a towless pump has a structure of 2 chiral bands with right and left movers. Each winds around the quasi-energy, quasi-momentum torus. In the state where the electrons fully occupy the left moving band, the current is proportional to the integral over the band velocities of all the occupied states and therefore must be quantized. Here we focus on a metallic regime. In this regime, the electron-electron interactions play an important role in the dynamics of the system. In the weakly interacting case, the dynamics can be described on the level of collisions between quasiparticles. Intra-band scattering of the quasiparticles is expected to thermalize the distribution within each of the bands. It can be shown that in the slow driving limit, the interband scattering is exponentially suppressed because of the phase space separation between the right and left chiralities. This scale separation gives rise to a quasi-steady state in which each of the Fouquet bands reaches an infinite temperature state, yet the entire system is not equilibrated. For example, in this figure, the left chirality band is occupied and reaches an infinite temperature state, whereas the right chirality band is empty. In this case, the current normalized by the particle density will be quantized because every momentum state with the left chirality contributes to the total current with the same probability. So far, we discussed the weakly interacting regime based on quasi-particle collisions, but can the quantization of current persist in a strongly interacting system in which the quasi-particles are not well defined? Well, in the strongly interacting regime, it is more instructive to use the Green's function description. The current in this description is defined by the following formula, where the expectation value is essentially the lesser Green's function evaluated at equal times. In equilibrium, the lesser Green's function is related to the spectral function by the fluctuation dissipation theorem, which says that the lesser function is given by the spectral function times the Fermi-Dirac distribution. However, for a driven non-equilibrium system, there is no simple relation like that between the lesser and spectral functions a priori. Furthermore, equilibrium Green's function depends only on the time difference for each momentum, which can be converted to frequency using a Fourier transform. In the non-equilibrium case, the functions also depend on the center of mass time. As a warm-up, let's discuss the non-interacting spectral function of the Thales pump averaged over the center of mass time, shown on the right figure, and compare it to the spectral function of an instantaneous Hamiltonian, shown on the left. The instantaneous spectral function, as a function of the frequency and crystal momentum, is peaked at the energies corresponding to the instantaneous bands. In contrast, the spectral function of the driven system got a tilt corresponding to the chirality of each band and developed side bands, as is expected from the Fouquet spectrum. The tilt shifts the peak of the function by the drive frequency as the momentum sweeps across the Brillouin zone. The spectral function can be separated to the spectral functions projected onto the right and left chiralities, which we denote by GR and GL. Okay, now let's take a look at the spectral function in the presence of interactions. The smearing of the function is related to the finite lifetime of the quasiparticles. In fact, for this interaction strength, the sidebands cannot be well resolved, meaning that the quasiparticle lifetime is shorter than a single period of the drive. The right figure shows the lesser function in the quasi-steady state. It suggests that the lesser function can be approximated by the left chirality projected spectral function GL multiplied by a constant, as is given by this formula, with FR is 0 and FL is a constant. This relation is the analog of the fluctuation dissipation theorem, but for the quasi-steady state. We have analytically showed that this form of the lesser function is a steady state solution to the kinetic equation up to exponentially small terms. We also analytically showed that this form of the lesser function yields a quantized normalized current. Importantly, it does not rely on the single particle picture and therefore can be applied for a strongly coupled case. To simulate the exact thermalization dynamics closer to the thermodynamic limit, we considered a model of a Thales pump with SYK interactions. This type of interactions allows us to simulate exact time evolution of chains as large as 100 sites. Here we model a chain of SYK dots with n fermionic flavors each, interacting with random interactions. In the limit n goes to infinity, the Green's functions describing the system have a simple self-consistent relations, which we solve numerically at each step of the time evolution. We initialize the system in an equilibrium state at t equals 0, and then evolve the Green's function with a time-dependent interacting Hamiltonian separately along the t and t prime domains using Kadanoff-Boehm equations. So using these exact numerics, we measured the current averaged over a period normalized by the total particle density. Initially, the current is non-universal. However, once the quasi-steady state is established, the current reaches the quantized value. In the further evolution of the system, the current decays because the system slowly thermalizes to a global infinite temperature state. We also studied how the system approaches the quasi-steady state. We defined the distance to equilibrium as a measure of how close the lesser Green's function projected to the left band is to the optimal equilibrium distribution. By definition, the distance to equilibrium is 0 for an equilibrium distribution. The left figure shows the distance to equilibrium as a function of time. It exhibits a jump at t equals 0 when the drive has started, and at later times decreases back to 0. This decrease indicates the thermalization of the distribution to a quasi-steady state. The effective temperature associated with the state is shown in the right figure on the log scale. The distribution approaches an infinite temperature state exponentially fast, and the thermalization rate is faster for stronger interactions. To summarize, we have demonstrated the quasi-steady state in a metallic interacting Thales pump. The quasi-steady state exhibits a universal current even when the lifetime of the quasiparticles is shorter than the driving period. Furthermore, intraband thermalization of the Fouquet bands to an infinite temperature helps stabilize the universal current. Finally, we have demonstrated a numerical technique that allows to exactly simulate thermalization in strongly interacting driven systems on a large scale. So with this, I would like to thank you for your attention, and I'm looking forward to your questions in the chat window. Thank you.